Hello, my name is Mario Duenas, and this is my lab report for Lab 3 in physics. The purpose of this lab was to assess the motion of objects while orbiting other objects, aka look at their centrifugal force. The first part of the experiment made us find the mass of a black hole, given that a star was orbiting it, while the second part made us find an initial velocity for a spaceship and a system with a moon both orbiting a planet. The following diagrams are basic explanations of what we wanted. The elliptical orbits of satellites was similar to the elliptical orbit of the star or the spaceship around the center object, which remained stationary. The bottom one is more in depth on the moon orbit and also shows the components in which acceleration pointing inward and velocity being perpendicular to that, or parallel to the moon's motion. In order to simulate the orbits in both parts of our experiment, we used GlowScript. No tracker was used because, well, we are on Earth, and on Earth we can't really simulate an orbit. At the end of the experiment, after various changes to both starter codes and GlowScript, I found that the mass of my black hole was about 7.19 times 10 to the power 33 kilograms, and one of the starting velocities that didn't make my spacecraft crash was the vector negative 750, 650, and 0 meters per second. In order to look for the mass of the black hole in part 1, we had to use the starter code which was given to us. The only thing we had to first input was our emo in order to get a specific seed. That way we would have designated orbits. And then we included the star's mass, which was 2 times 10 to the power of 30 kilograms. After this, we just fixed the while loop and solved for each thing individually that it told us to solve for. I'm not going to list every single thing, but I will point out that fnet parallel was equal to the dpdt of parallel, which is equal to dmag pdt times p hat. And then to find fnet perpendicular, we just simply did fnet minus fnet parallel, because that's an equation that was given. Here, to calculate the mass of the black hole, we put the mass of black hole is equal to the magnitude of fnet times r over the universal gravitation constant times the mass of the star. From this, we got a list of potential masses for a black hole, which were given for every spot in the orbit, and we simply averaged this list and got 7.189 times 10 to the power of 33 kilograms. For part 2, we used another starter code in order to assess the spaceship's orbit around a planet, which also had the orbit of a moon. One of the lines that it did end up switching, even though it said not to switch, was delta, which was first set to 30, but I changed it to 600 because the simulation was running too slow and it was crashing my computer. Additionally, as you can see on my screen, the velocity that I set on was negative 750 for the x direction and 650 for the y direction. In order to see how each object affected each other, we had to find the forces on each object from each other object. The only thing we didn't do this for was a planet since it was stationary, but we did it for the ship and also for the moon. Then we did the position update formula for the moon in order to find the moon velocity and the ship's velocity, and we also updated the position based on that. If the moon and the ships collided, it would say it would crash. But if the ship collided into the planet, it would say it also crashed into the planet. So in order to not get that, we had to trial and error a velocity that would work along the planet, but also wouldn't crash into the moon. Some error that could have occurred in this experiment could be the change in delta that they told us not to change, or just the vector directions being mixed up, which could cause us to have changes in our orbit, but I think I did that correctly overall. The net force and its components are different from the rate of change of momentum and its components because of the way you calculate it. Mathematically, they are both the same, but when you calculate the rate of change of momentum, you do so by observing the star's motion, and then you use that to find or to infer the invisible net force or gravity acting upon it. If a black hole and star were added to the system in part 2, that would mean the black hole would be the stationary one, and the planet would no longer be stationary, but rather orbiting along the star. The forces in the system would also not all be of equal importance. For example, the forces between the black hole and the moon will not be as strong as the forces between the black hole and the planet, just because of the increase in distance or just the increase in the negligence for each force.